Okay, so this week we're glad to have Jit Wu Yap from MIT, who will tell us about uniform boundedness of torsion points for abelian varieties over function fields.
So thanks everybody for coming and inviting me here. So I want to talk about some recent progress, it's not archived yet, on the so-called uniform boundedness torsion conjecture for abelian varieties over function fields and characteristic zero. So let's just say over the complex numbers. And we have this assumption that it's semi-stable. So all this is on work with Nicole Looper, who's at Brown now. So let me just start by the setup. So K is a function field of curve B. In this case, it's easy to say what a semi-stable means. So A over K, abelian variety. And then A is semi-stable. We say A is semi-stable if there exists a semi-abelian scheme. So if there exists what I call G over B semi-abelian. So it's a semi-abelian scheme. I will define what is it. It may not be too important. Yeah. So this talk such that the generic fiber so is isomorphic to it. So the focus of my talks will be on these semi-stable abelian varieties. And for those of you who don't know this sort of things, this is not too bad of an assumption. So remark, because we are in characteristic zero, if the torsion points, the three torsion points are in K, then A has semi-stable reduction. So this is a difficult theorem of Grothendieck. And basically, if you don't have semi-stable reduction, you can pass to some finite extension whose degree is bounded in terms of the dimension of the abelian variety. So, okay, let me write my first theorem. Theorem 1, Looper. So we have the setup KCD. And I'm going to fix G more than or equal to 1. This will be the dimension of my abelian variety. And GB is going to be the genus of my curve. So I'm going to abuse two G's. But hopefully this will be not too confusing. Then there exists an N, which depends only on G, the dimension, and the genus of the base curve, such that for all, let's see, for all A over K semi-stable, so dimension G, semi-stable. And we have to put some assumption that there's no isotriviality, so no isotrivial sub-abelian variety. So under this case, we can say that the K torsion points, we can uniformly bound the order. So then, let me continue here. X in AK torsion implies the order of X is at least M most N. So this is what we mean by this uniform boundedness conjecture, which is maybe the key theorem that we really want to prove is over a number of fields, but we do in an easier case, which is the function field case. And so we want to ask for uniform bound on this on the order of a K rational torsion point. So we have this semi-stable condition. Okay, I'll talk more about it later. So we have two theorems. So this is the first one. And I like to abbreviate this by calling this UBC. So uniform boundedness conjecture. And the second one is what I like to call a Lang-Silverman type statement. Again, and this maybe I call Lang-Silverman. So in this case, we have the same setup. So again, A is going to be a dimension G, semi-stable, no isotrivial abelian variety. Again, then the exists C. Depending on the two quantities, more than 0, such that if you have a K rational point, but now you are sort of interested in the opposite scenario. We want X not just to be non-torsion, but also like somehow a generic point. So we ask that you take the Zariski orbit, so let's just say Zx. Sorry, you take the forward orbit, so X, 2x, 3x, and so on. And let's say this is Zariski then, so the Zariski closure of this is A. Then we have a lower bound for the canonical height. Then the neuron Tate height for any L is at least C times the faulting height. So in the function field case, you can make an analogous definition of the faulting height. The neuron model still exists because the dimension of B is 1. And then in the function field case, you just take degree. There's no Eric Kirchhoff theory coming in. So this is the stable faulting height since I assumed A is semi-stable. That's what we call it. So we have two theorems. So this is over number of fields of conjecture by length for elliptic curves, and then Silverman make the appropriate generalization to abelian varieties. So we have both of these theorems. So the first one I call UBC, and the second I call Lang-Silverman. And I want to mention something which is okay, first, there's this semi-stable condition. We are trying to remove it now. We are maybe somewhat optimistic, I don't know. Somewhat optimistic, but I don't want to claim it right now. And secondly, you can think that, okay, I said semi-stable is quite a mild condition. You just take a finite base change. But the problem is that our bounds depend on the genus of the base curve. So you can imagine, even if the degree 2 cover, the genus could grow arbitrarily large because of the ramification is not controlled by the degree of the cover. So somehow this is the problem when you want to pass from a non-semi-stable abelian variety to a semi-stable abelian variety. So this is what I think is the key problem. And one feature of our proof is that it's an arithmetic proof. So there's only one point in our proof where we use the fact that K is a function field, and we invoke this, what we call an Eric Kirchhoff inequality, which is due to four things in 83 and refined by Delin. In 87, and Delin gives like a precise constants, but I just once mentioned it, so it just says let's just say theorem. So if A over K is semi-stable, and you let S be the places of bad reduction, then you actually have like a lower bound the number of places of bad reduction we have. So then S is at least, so let me write the other way around. You have upper bound the faulting side of the abelian variety by some constant C, some S, some the genus of the base curve plus 1. For some C, depending only on G, for C, let's see G. So there's this Eric Kirchhoff inequality that we use in our proof. So here, I should say KCB. That works only for function fields. I mean, so far we only know it for function fields of characteristic 0. And it's sort of saying that, okay, if I fix the dimension of my abelian variety, and I fix the genus of the base curve, and you let A get more complicated, the heights increase, then the number of places of reduction has to increase proportionally to it. There's no way out of it. Yeah, so this was first sort of proven by four things.
And C of G is effective.
Yeah, it's effective. So I didn't want to write it down, yeah. So faulting sort prove it for Jacobians, and then maybe the Enderlin sort go down a more improved version later on.
Fine.
Yes.
Is theorem one known if you replace the base field with a function field characteristic P, but not over a global field of
I
characteristics?
mean, actually, no, it's not known. So only for elliptic curve is known.
No, for elliptic curve,
But Abelian varieties is not.
not known.
Yeah, and the elliptic curve case was after Mazur's theorem. So it was known only in the 2000s
Yeah.
by Punnett by beyond Punnett. So, any more questions?
And the reason you are not attacking it over, say, FP bar of T
The main reason is
is because of
this. Yeah, this is a false actually for characteristic P.
Yeah.
I mean, I have reasons to believe maybe if A is an ordinary abelian variety, maybe this could be true, but then it's still open. It's still not known in this case. It's known that if you take super singular ones, it's actually false. So theorem, this error called A equal to is false for positive characteristic. Yeah. And so the claim I want to make is that, okay, you can make the conjecture of a number field, so let's just say conjecture. And I will just call this higher dimensional spiral. A spiral was the one who made this conjecture for elliptic curves. Okay, you can make the same thing. So, so let K be a number field now. And A over K is semi-stable. And you can S is the places of that reduction. Then, okay, you just made the same statement, but maybe I make it a bit weaker. I just say the constant can depend on the number field itself. C equals CK, G one. So in this case, it's a bit more precise that it doesn't really depend on K, but the genus of the base curve. So you can make this higher dimensional spiral and in the analogous fashion. And then, so what our proof shows is that this is enough to solve theorem 1 and 2 for number fields. So,
Sorry, well, for over a function field, the faulting's height means what the degree of the.
yeah, so you take the number 1 model, you pull back, you just take the geometric degree.
Okay.
So in the number field case, you have to take the arithmetic degree of the. You put some metric on the Archimedean place for the number field case, but over function fields, it's just the geometric degree.
And this higher dimensional spiral, you're saying that if your abelian variety had just one bad prime, but it's a colossal prime.
No, that's not allowed. Yeah, that's not. So so then even if it's a colossal prime. Oh, you are right. That's okay. Sorry, yeah.
You're saying that somehow the faulting's height still won't be big.
You are right. So I should really say yeah, it should really be summation of.
Okay, good.
Yeah, you are right. Yeah, perfectly right. So here, because in the function field, every prime is sort of the same size. But in the number field, I should weigh it differently as the prime gets bigger. Yeah. But the main thing here is that you just take the sort of the radical of the prime, you just take one exponent, you don't allow higher you don't really consider the exponent dividing the faulting side. Yeah. So then my claim is that our claim is that the conjecture, so claim higher dimensional spiral implies theorem 1 and 2 for number fields. Okay, yeah. So but the problem is that this is actually a very difficult conjecture. So remember, for G equals 1, this implies ABC. So yeah, the spirals implies ABC. And so ABC is known to be kind of very easy in the function field case because we have differentiation. And so we have to use like the higher dimensional spiral. So maybe this is not the correct way to approach. So maybe very difficult. So this might not be the correct way to approach in the number field set. Are there any questions? So I want to describe, some previous work. There's a lot of work done on such results. So yeah, so there's a famous Mazur's theorem. So let me just talk about UBC kind of results first. UBC. So this is just regarding the bounding the torsion point, but nothing about this the rounded height of a non-torsion point. So for G equals 1 and rationals with Barry Mazur in 77. And then for general number fields, so G equals 1, there's a series of results. So Camioni in 92, and then Camioni Mazur in 95, and then Morel Mazur. And Morel in 96. So Camioni first did for quadratic extensions, and then Camioni Mazur did up to degree 8, and then Morel just did for all degree D number of fields at once.
They bounded the entire torsion.
Yeah, but if you bound the order, you bound the entire torsion.
You know that.
You mean my result?
Yeah.
It's what, so mine is not ineffective. Maybe that's what you mean, yeah. So later I'll explain why it's not ineffective. So at some point I will use some ultra filters going on to this. That's where the ineffectiveness will come. So for their result, it's all quite, Mazur definitely very effective, and the rest are, Mazur's results optimally, but you can find everything, yeah. So just this upper bound still, and then ours is ineffective, yeah. And then higher dimensions, I want to say there's this for CM abelian varieties. There's a work of Schubert. In 88. And then there's some work of Kedoret and Tamagawa, which I think maybe I didn't really fully understand what they proved, but it's something about uniform boundedness or as the abelian variety vary over a curve. Well, I won't state exactly what they proved because I'm not too sure myself, but they have some results in the higher dimension. So these are 11 and 12. Okay, and then for function fields, we have more results. So let's say now UBC, but K is a function field of our characteristic 0. And then for G equals 1, it was known by Levin. So I actually managed to find this. People don't really cite it, but it's known before Mazur's result in 68. And then there's some results in higher dimension. Let me say for G more than equal 2. But instead of bounding the order of the torsion, you ask for full level n structure. So what this means that you ask if G more than equal 2 and you ask for all the n torsion to be K rational. Well, over here is known to be easier, and this actually sort of fully proven in this case. So let me just say, in this setting, there's Nadal in 89, and then Huang To in 06, and then Brunabart in 2020. And then there's one result I'd like to mention, which is Becker-Zimmerman.
In the function field, in Levin's theorem, for example, there's nothing like the winding quotient that Morel uses, right?
Is that like the what?
What Morel did to solve the problem was he looked at not the Eisenstein quotient, but the winding quotient. That's completely invisible here.
Yeah, so I don't think no. I think he did some kind of easy argument. I actually never read the paper, so I cannot comment. But it's in 68, so before definitely not the same method Maser uses. Definitely not analyze. So I mean, in this setting, in the function field case, you have the modular curve parameterizing the points, and you just want to say the gonality goes up or the genus goes up. So it's much easier than the arithmetic case.
Sorry, what is this like the higher genus results you're citing and ask for AN and AK?
So you do sorry, maybe I messed up. So you don't ask for bounding the order of torsion point, but you ask for whether can you bound the largest n so that all n torsion points are k rational. So it's much you can think of it as a much stronger condition than just asking for one torsion point of one n torsion point to be there. And then in this case, they're actually full results. Okay, I guess I didn't mention, but this is for genus of the curve is 0 and 1. And then this is like all cases. So they actually have a uniform bound on the torsion in this.
Wang Tao use kind of geometry, right? They use these
and
differential geometry.
Same for Brunner, but they use hyperbolic geometry and hyperbolicity arguments.
Particularly, as you said, to confirm the gonality.
Yeah. And then and finally, the last case for in the function field is Becker-Zimmermann. In 18, where they prove the full UBC, so let's say UBC for A having real multiplication. So for this one, they don't look at the level n structure, but just any torsion point, and they can uniformly bound the order of the torsion. So one thing I want to say is that so this series of results in higher dimensions, along Becker-Zimmermann, they use hyperbolic geometry, and to understand the moduli space and try to bound the lowest genus of a curve living in it. But so in that sense, you kind of expect to apply the number theory. So ours is arithmetic. So so that's why if you assume this higher dimensional spiral, then you can possibly say something number field case. But I just wanted to point out that we actually use hyperbolicity here, which is the proof of the Arrow-Clarke inequality uses hyperbolicity. So we're still using it at some point. It's just that we are minimizing our use of it. Yeah, that's how I would say our result is like. And just before the end, I'll just say in characteristic P, probably the best result is Poonen in those things. Poonen for G plus 1. Yeah, so here you want a bound independent of the characteristic of the prime. So if your bound depends on the characteristic this was known, or independent, the first one might be on Poonen. And there's this Lang-Silverman type theorem where you bound the canonical height. So Lang-Silverman. In a number of few cases, still completely unknown. Then for G equals 1, and function fields, this is done by Hindry-Silverman. In 88. And they show that if you assume ABC and spiral conjecture, you get a number field version. Yeah. But for function field, they have it completely. And our proof is really, you can think of as a direct generalization of Hindry-Silverman's proof. So you have to generalize everything appropriately and find the correct generalization, but you can really map the argument one-to-one in some sense to Hindry-Silverman. Okay, are there any questions before I move on with talking about the proof? So before I start talking about the proof, I want to say, you know, maybe some heuristics. Like why should we believe UBC? And maybe there's maybe not a nice reason. I mean, of course, you know something is finite, and then you hope that it's uniformly finite when you vary in a moduli space. So, but maybe that's a bit naive. And so our proof is really coming from this sort of heuristic. Let me just say heuristic. So, in our sense, so there's somehow two things that are in tension here. So the first one is that we are dealing with k rational points. So let me just say this off. So k rational points of A, and you combine it with what I call the Arikov inequality. So later you'll see, but we sort of can control it so that let me just say it places some constraint in geometry, it places constraints on where the points constraints on where points. So this works for any k rational point. But then now we now use the fact that we are dealing with small height points. So small height / torsion. So it's known from Arikov theory, so from things like Spiro, Umo Zhang, and many other people, that this sort of points want to actually distribute. So what do I mean by this? So collection of them. So yeah, whatever. So if you take any collection of such points, and they are Galois stable, so in this case they are k rational, so they are always be Galois stable, they want to equidistribute. But yet in step one, I sort of force it to not be able to equidistribute. I can say some condition on where the points lie, and then you have this tension between the first and second step, and then you get a contradiction if you can control things uniformly or quantitatively. But this is like the heuristic behind the argument. And so I said our proof is a generalization of Hindry-Silverman. And I think there's like maybe two new tools that we sort of introduced. So the first one is that we use what I call a higher dimensional transfinite diameter. So higher dimensional transfinite diameter. But this is something very ancient in potential theory and etc. But I think the usage of it is kind of new in Diophantine geometry, which is what we do. And so what we do is sort of we have a quantity, so let me just say briefly, it's a quantity that measures how close a set of points is to a lower degree hypersurface. So example, a quantity that measures how close 6 points are to a conic. How close 6.
Do you have Rumley's work, something like that, or
What?
just from
Yeah, exactly. Yeah. So Rumley did some things using this. Yeah. Robert Rumley. Yeah, definitely. Yeah.
he was looking at bigger fields, like to make real points in.
Yes, because looking at the Paquette-Segal style theorems. Yeah. I think. Yeah. It's related to transfinite diameter. But I think he was very interested in the case of curves, maybe. And the higher dimensional case was not so known at the time. I mean, I think over complex numbers it was known, but over non-Archimedean it was still mysterious at that time. So I won't explain too much, but let me just say, like given 5 points on P2, you know it lies on the code. There's maybe a unique conic passing through them if they're general. But what we want to measure is given 6 points, how close are they to a conic? And so this is a quantity that measures this sort of phenomena. And the second thing I will use is that we use that is new. It's what we call degeneration by ultrafilters. So I want, if I have time, I will mention this at the end of the talk, regeneration backward. But what we want to do is somehow obtain uniformity, control over certain things, certain quantities. And here's somehow a new trick that we know, which is that what happens if you are given a sequence of Abelian varieties over, so Kn here is a value field. And through this process, you will take what we call omega limit. Omega here is an ultra filter. On N, and we actually output a limit Abelian variety that lives over some very big field. So we call it maybe the Robinson field. And this will be non-Archimedean and etc. So omega limit plus, let me say, some rescaling. So one thing people who know modular will find funny is that if you have some Abelian variety, if a sequence of Abelian varieties and they go to the boundary, you should get a semi-Abelian variety. You don't expect an Abelian variety out of this, but we have this rescaling trick that goes back to Gromov in geometry, where you saw, I won't explain too much, but you sort of scale the norm away. So that, because the distance function measuring the Abelian variety to the boundary depends on the norm, and you rescale it so the distance becomes far again. And when you do that, when you take the limit, you get back an Abelian variety. You still somehow remain in a moduli space. Yeah. So if I have time at the end, I will explain more on this ultra filters. Yeah. Any questions? Also, I would like to just explain Hindley-Silverman's proof, and then I'll just say some words on how to generalize everything in there. So the first step is to use the Arekelov inequality, which corresponds to this first step here that I constrain where the points live. So the first thing is that which is the first, so let's say proof of Hindley-Silverman. So we use the Arekelov inequality, and it says we have a lot of places of band reduction. So let's just say there exists a M.
Sorry, are we doing the UBC or the Lang-Silverman, or which part are we?
Both, I guess. The proof again. So our proof, we don't do, what we really do is we bound the number of small points. Once you can bound number of small points, function points are 0, so we get the order. And then the lower bound of the Norante height is also given. So you sort of do both at the same time. Yeah. So the first step is that there exists n more than 0 such that the number of places is more than half the elliptic curve over m. Okay, this forms the Arekelov. So for elliptic curve is Riemann-Hurwitz. Just say that. And then the second step is that so for some t inside S, and t is at least S over 2. So it's quite a big set of places. If you look at the local height of E, so each of them is more than 0 because it's band reduction. So let's say for some t, and then for all v in t, the local height is at most 2n. And this is clear because if all there are more than 2n, we just multiply by t, and you get something more than high elliptic curve. So what we are saying is that we have a lot of places of band reduction that are not too bad, they are very thin. We have like bounded band reduction.
Sorry, what is lambda v?
Yeah, I don't want to explain, but you can think of the 4 things of the elliptic curve, you can express it in terms of some local heights, just like the height case, and then lambda v is somehow measuring how bad the reduction is at v. And so the reason why I want this is that so lambda v less than 2m. This implies that the neuron model, so let me say, number of components of ns, so of nsv, so let's say of n and s, is bounded by D. So what's N? So N here, I will let it be the neuron model of D over K. So in this case, it's like semi-abelian. So the identity component is semi-abelian, but the number of components could be arbitrarily large. And we can show that this is controlled by this lambda BD. So NS is the special fiber. Right. So what we are saying is that once you control the how bad the reduction is, then number of components will be bounded uniformly. So this can be done in elliptic curves. You can just check Silverman's book. For Abelian varieties is doable too. And so now what we do now is that given our torsion, let's just say the torsion or whatever. So our rational points, let's say small. We're going to multiply, I guess in this case, an elliptic curve. So multiply by xi, multiply by d factorial. So you consider d factorial times all these points. And so we can assume, since d is uniformly bounded, we can assume for all v in t, xi reduces to the identity component. And this achieves our first step of saying we control the geometry of these points. So let me explain why we say this. So it's known that so we're working non-Archimedean. So now this makes sense in the Archimedean place. But when we do non-Archimedean geometry, we should look at the Bokovic space. So here's a picture of the Bokovic electrification when V is bad reduction. V is bad reduction. So there's some sort of a skeleton in the middle. So there's a circle, this isomorphic circle, which is R quotient by Z. And so there's a root here. And there's like, for each branch point, there's like infinite trees sticking out. And there's like a lot of branching. But this exact point, or this exact circle, this set of points that connect to this sort of tip, this will be exactly the points that reduce to the identity component. So what we have achieved is for many places of V, a lot of them, we have forced the points to lie on this very small region compared to the entire Bokovic space. And this will somehow get a contradiction with this fact that small height points want to equidistribute. So by that, I mean that the points should somehow live evenly spread across this circle. So let me just write down the math. So for elliptic curve, it's really simple because we have explicit formulas. So in this case, let me just write down explicitly what Hindry-Silverman does. So the first thing is that, so we consider this guy. So if you sum it over all mk, and you sum over I not equal j, you look at the so-called local neuron Tate height of xi minus xj, and you normalize it. So this guy is shooting about it just like log x minus y. So as x approaches y, there's some sort of logarithmic pole coming in. And this from height theory, because we sum over all places, this will give us the neuron Tate height of xi minus xj. And let's just say this is 0. So this is 0 if xi all torsion. So let's just deal with the torsion case. So if you're all torsion, the difference is torsion, and then the neuron Tate height is 0. And so what he does now, he splits up the two sums. So you split up the two sums. The first one you sum over the places in T. These are the places when you reduce to to this thing. So let me say, and summation I naught equal j. And then you sum up on the other places. S naught and t. Maybe not, I mean, so mk naught t. Okay, so for the first time, we know all these points will lie in this sort of region, and it's easy to show that this is at least 1/12 summation lambda VE. So you can do this just by explicit computation on what the formulas are, because the elliptic curve, there's explicit formulas. And the second one, there's a nice lower bound for this. So it's a negative, and it's like log n over n times the sum of lambda v. And then v in mk over. So this is what we call Elki's inequality. But I learned from Shou-Zhang it's really by him, so I don't know. Yeah. So yeah, so but in literature it's called Elki's inequality. So this is what we call Elki's. But you can see here where the contradiction, because the first term here, we assume that we have a lot of places in T. So if you combine them,
I think Lang calls it Elki's.
then calls it Elki's, but Shou-Zhang said it's really T.
Okay.
So he said that, I mean, Elki's was an undergraduate in Columbia.
I don't.
Shou-Zhang was a graduate student, and he said he gave him the idea. So he told me this on Tuesday, so I tried to. But yeah, you can see the contradiction now. So at the end, what you have is 0 is more than or equal 1/12 summation v in t lambda ve minus log n over n of the rest. Let's just make it okay, but the first guy, we assume t is very big, right? So t is at least s over 2. So you get he over 24n. And here I can just bound it by log n over n hd. And then that's the contradiction. Once n is large enough. For n, and n is uniform. So this is the proof Hindris, Roman give, and you can sort of convince yourself that it's not necessarily the points with torsion. There could be small height, and you can bound the difference of bound the height of the differences. So to generalize this, we need to Abelian varieties. It's actually not clear what the correct replacement is. And this is quite recent due to Nicole, so let's say, to generalize to higher dimension. So I want to give the definition Abelian varieties. So Nicole Looper consider a certain function. So let's just say A over K. And L is a line bundle, so L ample line bundle. And then what we do is we pick the basis B of the global sections, the N of the global sections. And let's just say Cn is the dimension of those Cn's. Size of the N. So Looper defined the following, so by loop. So Looper in 24 to define a Hierarchical grid function, but you don't think of it as pairwise. So somehow in the dimension 1 case, this is like a red herring. So what this should really do is take in Cn many points, so number of sections many points, and output something. And so this is R. It's an actual number unless they lie on hypersurface, unless the points lie in diff S for some S in my line bundle. In which case it will be, in this case, this will be plus infinity. So you have two cases, either it lies on a lower degree it doesn't lie on lower degree hypersurface, then you get actual honest real number, or it does and you output positive infinity. And the main thing we really want of this is that when you sum up globally, it gives you something for the neuron state height. So the second property is that and you sum up over all B. Somehow the basis is not important, and you output normalized sum. So over Cn and neuron state height with respect to L of the X line. So exactly locally there's some choice, but globally when you sum up, you get back the neuron state height. So and the point is that now this, if your torsion point, this will be 0. And so what you want to do is to control this function or this quantity. So the first step was that the Alkes size, the Alkes inequality. This was generalized by Looper. So there exists a basis such that.
Remember, all kids use kind of a heat kernel.
Yeah, they use heat kernel, which is so in the non-Archimedean they use you can do the same thing in some of the Blasha-Berkovich, but only in dimension 1. So in this dynamical setting, so there's some dynamics behind the scene. She found some, I would say, an ad hoc way to prove this. So a priori, we should expect there should be some pluripotential thing we have to do, but that's too complicated, and we found a shortcut, which I think is quite amazing. But there exists a Bn such that this guy is always I just say less than equal minus log n over n times c, and c depends on c. And it's very explicit. We understand exactly what the dependence is.
You gonna tell us what G is?
Is G? This G? No, I won't say what G is. There's no time. Yeah. It takes someone to define what G is. Yeah. So yeah, so this sort of handles this part. So this part, the lower bound here is handled. What I need is really the positivity. And over here, equidistribution comes into our rescue. So okay, so for abelian varieties, we have a similar picture in higher dimension. So by Gubler, there exists what we call a skeleton of A, which is a real lattice. And again, it could be now it could be higher dimension. So in our case, it's a circle because it's one-dimensional quotient, not real lattice or real torus. Oops, real torus. But again, it has the same property that at this point, if you look at this region, these are points that reduce to the NA component. And so, and now that this, I would say, very nice theorem by Boxholm and Erickson. I say, theorem, Boxholm and Erickson. I think in 18. So it says the following. So we want to say that this Green's function, if all my points lie in this, then it's somehow positive, just like the 1/12 here. So it says the following. Let R be the retraction map. So there's a canonical map that retracts to the skeleton. V for the place V. And so let's say you have, I'll say vector Bn, which are points, such that if you put in the Green's function here, this goes to 0. So we know at least somehow it should be non-negative, pretty non-negative, like minus log n by n, but maybe it hovers around 0. Then it says it's an equidistribution phenomenon. Then the retraction of yn equidistributes to the Haar measure on the real torus. Haar measure on the real torus, on S. So what I mean is that look at the circle, then you get the uniform circle measure and the retraction must distribute to this. And so everything is true in the abelian variety setting. And so what we get immediately is that so it implies there exists a delta more than 0 if the points all reduce to the component reduced to identity. Identity component. The Green's function will be more than delta.
Right, can I ask first, just to, I can try to grasp
Yeah.
this. Suppose A had everywhere good reduction.
Yes, okay, sorry. So I mean this is bad reduction. So
Yeah, so,
skeleton would be trivial. Yeah.
right, can you talk us through the argument if it had?
Oh, this argument doesn't work. So we need a separate argument. So I can tell you the argument. Everywhere good reduction, Ericloff inequality, the height is bound, faulting height is bounded. And then in the number of few case, this is now done because the torsion points at bounded height, uniformly bounded height. So there's a good embedding, the theta embedding or whatever, and then in the embedding, does that make sense? So we embed A into Pn because the faulting side of A is bounded. You can bound the difference between the torsion, the neuron tail height, and the wave height. So
Okay,
yeah, so the neuron tail height minus the wave height is bounded in terms of some constant in terms of faulting side. So faulting side. It's just A plus 1. Yeah.
so you can't use the same argument that you're using?
No, it's a separate, completely separate argument. And I'm saying that in the number of few cases, the Ericloff inequality implies faulting side is bounded.
Okay, but I'm just saying, so this argument you say doesn't.
This argument will not apply to the everywhere good reduction. We have a separate whole 10-page to argue that case. Yeah.
That's interesting.
And the way to argue, we still use Ericloff inequality to say it's bounded faulting side. And then we run through the proof of lambda run now, because somehow in the function field case, there's no Northcott property. So we have to analyze something special about Abelian varieties. Yeah. Yeah, so this case only applies to when you have at least one case of bad reduction. But yeah, so in this setting, this is more than delta, more than 0. If the point, so for exists delta, and let's say n, so therefore all small n more than big N. So if you have enough points, then you have this positivity, and then you are done. But only for a fixed abelian variety. And so the challenge is to make this uniform. Make this uniform. Make it delta n uniform.
Before you make it uniform.
Yeah.
You said something about transfinite diameter in higher dimensions. What?
Yeah, so this is where Boxon-Erickson uses. So inbuilt to the Green's function is a transfinite diameter, somehow imbued to the definition. And Boxon-Erickson has this theorem that says that the points
Is it defined like Fekete at all?
yeah, exactly, the faculty. So if the points, but they have what we call, the theorem works not just for faculty, it works for what we call asymptotically faculty. So it may not be exactly the soup, but as you go to n, the difference between it and the soup goes to 0. Then you still have equidistributions. So actually the proof is similar to Spiro Umo Chang's proof, where you have small height. So exactly the small height is there's some leeway involved. Yeah, so that's why we don't have to assume our points are faculty. Just asymptotically faculty, which is what really this condition means. The asymptotically faculty. Yeah. And then the challenge to make this uniform, and maybe this is where this new technique comes in. When I will sort of maybe very briefly sketch it out. So it's a degeneration argument. We want to degenerate around the whole degenerate arbitrary sequences of abelian varieties. So what we do is the following. We let X be a quasi-projective variety. So in general, it's the moduli space of principally polarized level 3 structure. And then we fix a compactification, X bar. So the boundary is defined. And then with this is somehow, this is going to be defined as minus log of the distance to the boundary. So as you approach the boundary, this function will grow larger, but there's a logarithmic pole on it. And so here's the following. So now you let epsilon n, okay, so given a sequence an over kn, so this corresponds to spec kn points. So you have after you pick level 3 structure, spec kn to AG3 to X. And so you can define, so lambda n is defined, and you set epsilon n to be lambda n of a, sorry, lambda down boundary of an, and you inverse it. And then, so now you define the following Banach ring. This is the rescued, it's an ultra product of rescued, product of rescued norms. So you look at all sequences in Kn such that the supremum is bounded. So you look at all bundled sequence, but we allow this rescaling. So in this case, our coefficient is allowed to go to infinity as long as it's not going to infinity too fast compared to epsilon n. Because you can imagine epsilon n is going to be very small. And so here's like a lemma. It's not a difficult thing to prove. There exists a unique morphism, spec A epsilon going to AG3, such that this commutes. So this usually has a projection. And then here is the point defined by AN. So what happens is that normally when you try to do this, you will find that you will not end up the boundary. You will not end up in the moduli space, but you will end up in the compactification instead. And so you need to allow more invertible elements so that you can get a morphism from A epsilon to AG3. And this happens when you choose the scaling. So it's all chosen correctly so that you have this phenomenon. And you think of this as a family of abelian schemes now. I mean, it's an abelian scheme because it's a fine moduli space. And then for any ultra filter, so okay, I won't define ultra filter, but let's just say what's going to happen. Omega on n. There exists, you can define a norm on A epsilon by doing, you take a sequence and you output the omega limit now of this guy. So omega limit, so ultra filter layer take limits of everything. And the point is that this defines for you, so if you let kernel of omega be those with norm 0, so xn, and such that the norm, the omega norm is 0, you will find that this gives you a maximal idea. Then A epsilon over kernel epsilon, this is what I call H omega, is a value field. So the valuation comes from this omega norm here. And now the point is that then you have for this abelian scheme, you get a map from spec over H omega to AG3. And so you get what I call omega limit of the abelian varieties now. So somehow you can define, you can take an ultra filter limit of abelian varieties in this way. And I think personally the magic is that this AG3 is a fine moduli space. So that's where probably where all the hard work went in proving that abelian varieties are a fine moduli space. And so I don't have much time now, but using this is how we can prove uniformity results. So it's going to be something like we assume there's no uniform bound, and then you degenerate it. You take a sequence where it gets worse and worse. But now you can define a limit out of it, a subsequential limit. In our case, the omega limit. And when you just have to check on the omega limit, there is some delta. And this is true because, for every pointwise abelian variety, there is a delta in the end that we know. And so one catch is that H omega is general, it's very general. So it's a general non-Archimedean field, general rank 1. So even if you start with a sequence of DVRs, the limit could still be very terrible. And this is somehow actually important to us because in this groupless result, And this box of Erickson, it was first proven for discrete valuations only. But recently they broke the barrier and proved it for general valued fields, and we could just use their results. So everything is sort of set up for us. So I mean, 5 years ago, this would not be approved because we are missing both these ingredients of our valued fields. So I think I'll just end my talk here. Thanks everybody for listening.
It looks like you have a tool coming from ultra filters that allow you to get uniformity free.
It's not, yeah, but I wouldn't say for free. So we have to understand the pointwise case.
What are, I mean, you gave an example on Tuesday, you're giving this example.
Yeah.
Do you have others in mind? Do you have maybe a very simple example where we could understand this principle?
Yeah, I mean, I don't know. Like, that's up Eric off, so I can't really. I don't know. Yeah, but I want to say for any rational map, whatever, there's some sort of Eric ring function is pairwise, okay, and we know it blows up at x equals y, and so the question is that can we lower bound it? So you want to bound in Freeman in terms of like C times resultant of F. So something very simple like this. And then the answer is like yes, because so otherwise you assume you have a sequence where you have a sequence of points. So that is minus n resultant of F. And then now you degenerate with epsilon n. So pick epsilon n to be minus n resultant F inverse or something. Yeah. So when you degenerate omega, this is still non-zero. You get something -1. But you can show because this is growing faster than resultant, F omega has good reduction. And when you have good reduction, this function is going to be 0. And then you get the, yeah. So this, I think, to me, is like a simple example, but you have to know what this function is for it to make sense.
So what do we know, if anything, about, instead of torsion subgroup, the rank of the rank of the Mordell vector?
Yeah, this I don't know. I think this is still wide open. So yeah. So for me, the philosophy is we can control this because we have this trick where we know small torsion points equidistribute. So I think it's not true that if you take the points on the model V group, then it's going to be distribute or something. This is not a thing. Yeah.
Well, that's why I asked you about the winding quotient. The Hindry winding quotient has the property that the rank is 0. It's exactly the biggest quotient for which the model weight group is finite, and that's where he ran Maze's argument there, and then it worked. So instead of the Eisenstein quotient, he looked at this winding quotient, which is exactly that quotient. So there's this very big, much more natural object, which is rank 0.
Yeah, I'm just, it seems like the answer is no, but then the step in the proof simplify if the base, if the curve is genus like 0.
No. Yeah, so it's very general and just everything. I mean, we simplify the case where we do every regular reduction. I guess.
Is this, like in their work, or in the work of you were mentioning at the beginning, there was a gonality bound that had to be understood. Where's it buried?
So
Where's it buried in your work?
So my work has no gonality bound, so it's only a genus bound, which is weaker than gonality. But it's known that somebody told me, and I think it's true, that if we remove semi-stability, we get the gonality bound. But we have to remove semi-stability, which is which we are still doing. Ours is weaker. If we have gonality bound, then we can do the semi-stable extension, and we're just done.
All right, if there are no more questions, let's thank the speaker.